przyjemnej podróży.
Dear ladies and gentlemen,
Szanowni Państwo,
pleasure to invite to the stage Professor Edward Reynolds, Program Manager at Johns Hopkins University, and also the Project Manager for NASA Double Asteroid Redirection System, DART. And DART is a part of larger international effort focused on planetary defense. Warm welcome for Professor Edward Reynolds.
All right. Thank you very much. Thank you for coming. Let me start. Let me back up a little bit. So this I'm going to start with this image here. It's an artist rendering. This is the last moments of the DART spacecraft, which just over 2 years ago, we deliberately crashed it into the asteroid Dimorphos. And Dimorphos is a relatively, it's an asteroid that's the size that we're concerned about from a planetary defense of doing damage on Earth. It's about 150 meters in diameter. You're going to see that number a lot in my presentation, 140 meters, 150 meters. But the intent of this was to see if we could actually move it in terms of its trajectory. And with the intent that sometime in the future, if we saw an asteroid that was threatening Earth with an impact that could do serious damage to the population, we would be able to divert it from hitting Earth if we had enough time. So this was a test. It was very, very successful. And so as I get through my presentation will talk about asteroids in general, and then it will move into asteroid defense, and then it will we'll focus on the key aspects of the DART mission. So be patient with me, and you'll get to see not an artist rendering, but some real imagery that came from the mission, from both the DART spacecraft and from a little teeny tiny Italian spacecraft. It was this big. It was the size of a couple loaves of bread that followed us, and it did not crash into the asteroid, but it actually watched us as we hit the asteroid. So we got good imagery from that. And then just last week, down in Florida, we watched, this is all part of an international effort. I just kind of want to make that clear, that this is not a NASA or a US thing alone. This is a consortium. A key player in this consortium is the European Space Agency. But just last week, we got to watch in Florida the launch of the HERA spacecraft, which is the European Space Agency contribution to this overall mission, in which they are going to visit this asteroid and just look at the effects of the impact and pretty much put a bow on the science of using kinetic impact as a tool for planetary defense. So asteroids in our history are relatively new. So the first one was discovered in 1801, and logically it was big and bright, and since then we have discovered hundreds of thousands of asteroids. There's many in the asteroid belt. But there's actually asteroids that are very close in Earth's neighborhood, and I'll show you an image of that shortly. But it was really not until 1991 and 1993 that we actually got good images of what asteroids look like. And so you see, these were taken by the Galileo spacecraft as it was heading toward Jupiter and it was passing through the asteroid belt. It had multiple opportunities to actually image asteroids. And so it captured these images. The first one on the left is in 1991. And the one on the right is in 1993, and they're big asteroids. And so if you look, the asteroid, the picture on the right, you see a little teeny tiny moon. That moon is 5 times bigger than the asteroid that we hit with the DART spacecraft. So they come in all shapes and sizes, from very, very big to tiny, tiny, tiny. We get hit by asteroids every day. And we just don't know about it because they're the size of little pieces of gravel. So there's a whole range of asteroid sizes. Some of them have moons, some of them don't. So, the 90s were a busy period. So you saw the first images, 1991, 1993. This was my first asteroid mission. And if you look at that picture on the top right, that's the Near-Earth Asteroid Rendezvous spacecraft. That was a spacecraft that we built at the Johns Hopkins Applied Physics Lab. If you look standing on the ladder to the right, that is me with brown hair and more hair. I was young. I was one of the system engineers that worked that mission. This was just looking at doing science. We were not looking at asteroids as threats at that point. It was just science. What can we learn about asteroids? So we sent this spacecraft to the asteroid Eros. It went into orbit about Eros. It orbited the asteroid for 1 year. And then the mission was pretty much over. We had done everything we wanted to do scientifically. And so it was like, well, what do you do now? And we got we got a spacecraft in orbit about an asteroid. There was no harm in just landing the spacecraft onto the asteroid. So it was not even designed for a landing, but we kind of put it down in a 3-point landing with 2 of the points being the corners of the solar panels. Landed it successfully, and that's where it sits today. It's dead, it's long gone, but for 2 weeks we got the best gamma ray science of asteroids ever taken. So at this point in time, asteroids were just curiosities. We were just collecting images of asteroids. So every couple of years, there'd be another spacecraft en route to another destination, and along the way, it would pass some asteroids, and it would take pictures, pictures, pictures. So we've got a good family album of asteroid pictures at this point. We really, in the 90s, we knew that they were a threat. We knew that they had, in 1908, there was a big asteroid that hit Russia in Siberia. No one was really around it, so no one really, no one got killed. A lot of animals got killed. A lot of trees got pushed down for a wide area. But we knew asteroids could be a threat to Earth, but we had not really experienced it. And so this is kind of what our neighborhood looks like now. These dots don't represent hypothetical asteroids. Each one of these dots is a real asteroid that we know about, and we know its trajectory, and we track it. So this is our neighborhood. So there's lots and lots and lots of asteroids. So the chances are there that they do hit Earth, and that they are a threat to the population. But still, it wasn't until real recently, none of us, like 20 years ago, did any of you all have conversations, or when you opened up your news feed, you weren't seeing news about potential asteroids hitting Earth. And it's like every time I open my news feed at night now, there's always a story about a potential asteroid coming to hit Earth. And a lot of it is hyperbole. But it really, you think back, that was, even 5 years ago, we weren't thinking asteroids as a potential threat among the general population. It's just only recently. And so this is kind of the but. And so this is where asteroid impacts really got the public's attention. And this is 2013, over Chelyabinsk, Russia, it's a fairly big town, a 20-meter asteroid, 20 meters, think about that. That fits easily on this stage. It would fit on this stage. It burns up in the atmosphere, and it actually heats and it explodes in the atmosphere, creating a shock wave. And so people see the light burst, and they run to the windows. And they run to the windows, and they get to the windows just in time for that shock wave to hit the windows. So a lot of people went to the hospital because of broken glass. And nobody died. So 20 meters, it's a threat. It does real damage. It can kill people. But it's not the big threat that we worry about, like what killed the dinosaurs or what happened in Russia in 1908. But it did start the thinking of various organizations in different governments. Like, heads of governments would call their space agency or their military and say, what are we doing about this? How can we protect the public? So you're beginning to see the beginnings of coordinated planetary defense. We need to get together, we need to talk, we need to figure out how to recognize a threat, and when we recognize a threat, what are we going to do about it? So with DART it's not the beginnings of an asteroid defense program. It is coming along as one of the first tests to prove the viability of asteroid defense in conversations that have already been going on since about this time frame. So this is the United States government tracks fireball airbursts in the atmosphere for a variety of reasons. And so this is data that's been captured by US government sensors from 1988 to 2021. And so you can kind of see these are asteroid impacts with Earth's atmosphere that were large enough to create a fireball that were detected by US sensors. And that big red one that you see over Russia, that's Chelyabinsk. And so you do see, we do get hit by asteroids regularly. We get hit by asteroids every day. They're just tiny. But if you look at the data on the right of the graphic, you can see Chelyabinsk was 20 meters, and you saw the damage that it did. Tunguska, that was Russia, that was Siberia, 1908. That flattened trees for tens of miles. If there were people in the area, there certainly would be a mass casualty event. That was 60 to 190 meters in diameter. So remember, we hit Dimorphos, it was 150 meters in diameter. So it's not too terribly big, can cause a lot of damage. And then there was the dinosaur killer 65 million years ago. That was 10 to 15 kilometers in diameter. So we call those the planet killers. So the thing I need to assure you at this point is, at this point in time, with what we know of the asteroids that we know, we see no real threat to Earth for at least 100 years. And there's a blank spot below that. But what we also know is we don't know where all the asteroids are. So that's a good part of planetary defense, is just trying to identify all the asteroids that are of size that are a threat to the population of Earth. And so here's some numbers. So they're basically binned, and they, everything from 10 meters and under, we don't even really count. And then there's 50, asteroids that are 50 meters and bigger, asteroids that are 140 meters and bigger, a kilometer and 10 kilometers. If you look at the size distribution where it says, or the number distribution where it says how many, the planet killer, there's only 4 in the solar system total. We know where they are. They're not a threat to Earth. And so that's why you see the pie chart at the bottom. It's all white, 100%. We know where they all are. The ones that are about a kilometer in diameter, we know where 95% of them are. That's the good news. The bad news is there's 900 of them, which means there's about 45 that we don't know where they are. And then we get into, if you look, as you get smaller and smaller, that number goes up exponentially. So the good news is the ones where there's plenty, they're of a size, they're smaller than what happened in Chelyabinsk, they're really not worth worrying about. They're not going to do serious damage to the population, even at a regional scale. The ones that are big, we don't really worry about them either, because except for those 45, that 5%, we know where all of them are. And I'm going to show you shortly, very, very soon, we're going to know where all of those are, and we're making a serious attempt at what's left over. What's left over is the size of asteroids that are between 50 and 140 meters in diameter. And so if you're 140 meters in diameter, remember Dimorphos was 150 meters in diameter, we only know where 43% of those are. Those are big. Those can do real damage. And so I'll show you there's a methodology that's out there. There's actually multiple methodologies out there for us to identify the remaining asteroids of this size. And then we're beginning to come up with strategies to tackle the 50 meter in size. But again, as they get smaller, they become less of a threat, of a regional threat, and something that's more manageable. So here's what a 50 meter asteroid can do when it impacts Earth. So this is a crater that's in Arizona. It hit 50 meters in diameter. It creates a fireball that's 10 kilometers in diameter. It creates large animal kills at 24 meters in radius. Sorry, I'm saying diameter, but I mean radius. And then there's just hurricane winds when you get out to 40 kilometers. But it's really that 10 kilometers, or something that's as small as 50 meters, can really cause devastation that has a radius of 10 kilometers. So what does that mean to us who look at maps? And so if you look, it would take out Washington, D.C. If it hit Washington, D.C. square, the entire surface of Washington, D.C. is in that red zone. So it is still big, but it's a regional effect. So this is just kind of going and saying, right now, based on the charts I just showed you, if you're 140 meters and bigger, we know where 43% of those asteroids are. We have to go find the others. And so we've got ground telescopes. This is how we've been discovering them. So these are existing ground telescopes, and they're shown. There's a ground telescope called Linear, it's shown in blue, Catalina in green, and Pan-STARRS in yellow. And you kind of see we've discovered a lot of these asteroids with just these 3 telescopes. The key thing to look at, though, is the amount of data return that we're getting with this technology is waning. Those histograms are actually going down, and so we need a better technique if we're going to find all of them. And so what do? What's the best technique? And it's the quick and dirty answer is you put an optical telescope in space that can systematically scan the sky, and if you make the telescope infrared, not only can you find out where an asteroid is, but you can actually, using the infrared data, you can actually find out what size the asteroid is. If you're just looking at it with a visible camera detector, you just see a spot of light. You can't glean what the size of the asteroid is. So, short answer: put an optical telescope in space that can scan the sky with a infrared detector. And so this is what a spacecraft being built by NASA is going to do. And it's called NEO-Surveyor. And you see the sun in the middle of that graphic, and then you see Earth's orbit is shown as the dotted line, and then you see the fields of view of the NEO-Surveyor. And as time goes by, this is what it's picking up asteroids as they orbit the solar system. And if I advance this, our current state is 43%. Within 5 years, 43% turns into 66%. And then within 10 to 12 years, our 43% has turned into 90%. And these are all based on the specified performance that's required of that telescope. Typically what happens is the telescopes that do get launched have much better performance than the specifications. So these numbers are actually fairly conservative. So I think this thing's going to play out until it reaches the end of its loop. Okay, so by the late 2030s, you know, if you're 140 meters and bigger, which are those remaining 45 that we really worry about, plus a substantial amount of those 140 meters in diameter, we know where you are just with this one spacecraft. In addition to this spacecraft, there's a new asset coming on the ground in Chile called Rubin, which will be scanning the skies systematically also. It's just doing it on the ground at high altitude. This will be, this is an excellent tool for finding asteroids as well. So those two items working together are really going to take the uncertainty down to where we're actually tackling those 50-meter asteroids that we have a substantial number that we need to figure out. So this is kind of the near-term future of asteroid defense in terms of, you know, what are the known targets, and are they on trajectories that cross Earth's trajectory as it orbits the sun? So given that, this is the kind of the tools in the toolbox that, if you know where they are, and if you know that they are a threat to Earth, what do you do about it? And so this is, if you look at the x-axis, this is the warning time in years. And if you look at the y-axis, it's the asteroid size. And so these are different tools that are being developed now to deal with these threats to Earth if we know that Earth is truly in the crosshairs of one of these asteroids. And so one of the key things is, if you look at the bottom, it's not fancy, sexy, run into an asteroid and divert it. It's just plain old civil defense that if it's a relatively small asteroid that can cause regional damage, you know, it may not be enough time to actually do something about it, diverting it, but if you know where it's going to hit on Earth, you've got time to move people out of the way. And so that may be the only answer where, buildings get destroyed, infrastructure gets destroyed, but people can be moved out of the way, and then we rebuild. So that's actually one of the big tools that I'll show you later. We actually do these tabletop, we call them the tabletop exercises, but every 2 years we have organizations from all over the world that get together and they coordinate this type of activity. They actually go through drills where they will come up with a mock exercise where an asteroid's going to hit, and they deal with the uncertainty. Like at 3 years out, we know it's going to hit in this area, but we don't know exactly where. And a lot of it is just going through the trouble, you know, what are the issues of getting countries to coordinate with themselves and become, you know, cooperative. If you find out an asteroid's going to hit Earth, but you don't know where, everybody's cooperative. But if you find out it's not going to hit your country, or it's going to be on the other side of the globe, suddenly countries can become disinterested. And so how do you keep commitment if you know that, if countries know that they're not going to be threatened by an asteroid, to the point that they can actually assist countries that are in danger and help with civil defense? So that's a big, big tool. I showed you the image of DART. DART was a demonstration of kinetic impact. There are other more exotic techniques. Running a spacecraft into an asteroid is simple. There's nothing special about the spacecraft. It just has mass, and you run and you hit it at high velocity. For DART, we hit it at 6 kilometers per second. It was something about the size of a small car. There was nothing exotic about how we developed that spacecraft. The other techniques, there's ion beam deflection, in which you actually use a spacecraft to point an ion beam at the asteroid and use that ion flow to divert the asteroid. That's never been demonstrated, ever. And then there's nuclear. And nuclear has its own set of issues, but it's a tool for something that is very, very large and you don't have a lot of time. That is something that does need to be simulated and understood, but there's all kinds of treaty issues. It's actually illegal to detonate a nuclear device in space at this point. So how would you deal with it? So these are things that they address at these tabletop exercises. So the key thing with this graphic here is time. So you worry about how big something is, where is it going to hit, and then how much time do you have to do something about it. So you do get surprises. And so we have a surprise coming up in 2029 called Apophis. And so you see the trajectory of Apophis going past Earth. That's the geostationary satellites. It is it's going to go past very, very close to Earth. This is a good exercise in something shows up late. It's a great tabletop exercise of what would you do about it. It's also a good exercise in how would you if something arrived late, how would you characterize it? And I'll talk about that in a little bit. So you're going to hear the word Apophis. It's going to come up as we approach 2029. But key things to note, in 2004, that was when it was discovered. It was discovered less than 20 years ago. Well, just over 20 years ago. And then for the first several years after discovery, there was a real concern because when we discovered it, there was very little time to track it. So if you have little time to track it, you have very coarse tracking information. So for several years, we had a real worry that there was actually, I think it was almost a 3% chance of hitting Earth. It was only when we had an observation in 2013 that we got to track it more and for longer, and determined that it was not on an Earth impact trajectory. But so it's a good exercise as to something could come along, you only have 20 years, what do you do about it? And how can you get that information of how big is it, where is it going to hit, and how much time do you have? Get that discussion moving forward to actually do stuff about it. So this is the whole prepare to act. So there's this graphic again. I think I put this back into the slides just to make sure everyone knew about time and tools. So NASA and others have actually thought about this. What do you do? And the answer is it depends. So when we discover an asteroid, and we look at warning time, we look at impact probability, and we look at its size. You know, I talked about that internet feed. Like every night I go to the internet feed and there's like NASA warning, fireball heading toward Earth. And basically it's any time that an asteroid of any size, you know, basically 10 meters and up, and you saw the numbers, there's a lot of those. If there's a greater than a 1% chance of it hitting, they issue a warning. And a warning is just a warning. It's just they're flagging it. They're just sending an alert to say, hey, we're adding this to our catalog. NASA's definition of warning and the media's definition of warning that create headlines are much, much different. So when you see that, NASA warns, that's all that is. So just keep that in mind. If it's bigger or if the probability is greater, they do things like terrestrial preparedness planning. And that's just civil defense. Let's say we've got something, it's coming in less than 20 years, it's bigger than 20 meters, and it has a 10% chance of hitting Earth. Let's start planning civil defense based on this object. And then if it's bigger than that and has a probability of impact greater than 1%, they actually start looking at options. What can we do beyond civil defense? So just key things to map out is there are systems in place, there are tools in place, there are processes in place, they are coordinated, not just the US talking to itself, the US talks with people in Europe, they try to talk to people in Asia and Africa as well, but this is data that is shared, and so this is all coordinated. You'll see in some of these slides the words exercise, exercise, exercise. So this is part of just an exercise, one of those tabletops where they go through exercises of, we have something that's coming toward, and in this exercise, Dallas, Texas, and depending on size and depending on the makeup of the asteroid, is it metallic or is it just a rubble pile? The size of the damage changes and the response that we would do changes. So we need to know how big is it, what's its construction, how much time do we have, and what's the impact velocity. But so there's data that we need to develop the correct response. So this is part of that coordination. So this is under the auspices of the United Nations, and this is under NASA. There's what's referred to as IWAN, which is just basically trying to discover the asteroids and getting the data out about impact time, location, and severity. And then there's a separate coordinating group that's chaired by ESA, and there are participation of both ESA and NASA on both of these teams, but it's the coordination of what do you do about it. So this is key thing that planetary defense is not a concept, it's not an idea that is just being thought about. This is real stuff that happens all the time. So this is just an image of one of those tabletop exercises. If you look close in those slides, you see the words exercise, exercise, exercise. They have to do that because these slides go public, and a lot of times a public slide with the media, if they see something that's heading toward Texas, they don't want to scare the public. So each one of these slides has the word exercise, 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 just to make it absolutely clear. So this is just, they just had tabletop exercise number 5. So this is just imagery that was taken. If you look, they've got representation by NASA, by the IWAN folks, by the gentleman in the top right. He's one of the top people in FEMA, which is the United States' civil defense lead at the federal level. So the United States takes this serious, ESA takes this serious. In a lot of these planetary defense meetings, they'll actually try to, we're trying to pull in the other countries. And so one of the last, not tabletop exercise, but just a workshop, they held it in Vienna. And it was not because it was a central location, but they thought it was a good enough venue that would attract other countries to send people to actually participate in this. So that's one of the things that they're dealing with is just getting the interest from all these other countries that are dealing with other problems. So it's not that they don't care about planetary defense, but they also have other problems that they worry about. I don't know why this one's, let me bounce. Okay, so I'm going to talk a little bit about DART. So I actually got a little bit faster than I thought I would. So DART is kinetic impact. It's just running an object into another object, and it's billiard balls. The asteroids are very, very big. Spacecraft are very, very small, but if you hit them fast enough, you actually have an effect. And so this is the only tool in the toolbox that has been demonstrated. And so far, it's been successful. As tool validation, it's a successful tool. So I'm going to share a little bit. This is just a graphic of the mission in general. We launched it in November 2021, and for 10 months it cruised toward the asteroid, and in that 10 months we had to characterize the spacecraft so that we knew we could control it precisely. If you're, so you see there's actually 2 asteroids in this photo. There's a large asteroid called Didymos, which is 760 meters in diameter. And then the asteroid that we hit is called Dimorphos, 150 meters in diameter. And the geometry of this was, if you just hit an asteroid in space, the uncertainty of what was its trajectory before you hit it is much greater than our ability to move it. But if you hit a moon, it's very simple. If you hit a moon and you change the mass of the moon and you hit it with momentum, you'll change the orbit period of the moon around the asteroid. And so if you just look at the light curve, we look at asteroids in space with light curves, mostly to see if they're tumbling and if they have moons. But we could look at the light curve of the dot that represented these two asteroids, and it gets brighter and dimmer and brighter and dimmer, very, very regular. And part of that regularity is the tumble or rotation of the big asteroid. And the other dimming is the little moon is going in front of or behind the asteroid, and so the surface area of the reflection is getting bigger and smaller. And so you can actually measure the period of the moon about the larger asteroid just by looking at the dimming and brightening of the light. If you could change the period of the moon, you could very precisely determine how well you hit the asteroid. And that's exactly what we did. It's a precise measurement. If you hit the moon of a binary asteroid, you get very, very precise measurements. And so this is kind of the single mission on a slide that we showed all the time leading up to launch. You see the little Italian spacecraft there called Lychee Cube. 2 weeks before we hit, we actually we carried Lychee Cube with us. We kept the battery charged. We kept it warm. And 2 weeks before we hit, we ejected it, and it became its own mission. And it had to pretty quickly move away from an impact trajectory and get to a good viewing geometry so that it could watch us hit. And that was really, really nice to have that asset there. But then it shows, like on September 26th, which was just over 2 years ago, we hit the asteroid, and we hit it at 6 kilometers per second. We hit it dead center, and from the data, we moved it a lot. So this just kind of shows the schematic of what we were trying to do. That's the original orbit. This takes 12 hours, or I think 11 hours and 30 minutes. And then, darn it, I'm gonna go back. Well, yeah, we got time. It doesn't want us to go back. So
we're embarking on a new era of humankind.
Didymos and Dimorphos make a great target.
Discovered not very long ago.
We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3,
The
2,
key thing, we built this
1.
spacecraft during COVID, which is a story in itself.
Liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss. 4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
But now, Hera's going to, 2.5 years from now, Hera, which launched last week, will visit both those asteroids and determine number one, is there a crater? And then it will determine also something called beta, which is just the overall density and our ability to transfer momentum. But it's working together, NASA and ESA together is critical. And I believe one of the, Hera is carrying 2 CubeSats itself. One of the CubeSats is built in Poland, and then there's a lot of the subsystems on that spacecraft come from Poland as well. So this is just showing, this is the moon we hit. You can see it looks awful lot like an egg. Just looking at it and looking at the debris that we created, it's essentially what we refer to as a rubble pile, in which it's just small rocks that are held together by self-gravitation. So when we hit it, to me, I think it's almost like hitting a water balloon, that it actually, had a bit of a wave motion going on. But this just shows a close-up of exactly where we hit right between those 2 big rocks. And those 2 big rocks would fill this stage right now. This is that Italian CubeSat. So everyone looks at CubeSats and they think that they provide very limited science. They were the size of 2 loaves of bread, very, this big, literally that big. And in that is an entire spacecraft with a propulsion system, a radio, cameras. When we hit, everyone thought, it would just be a simple spray. Everything would travel out very linearly, and it would just almost look like a starburst. And with this data, everyone was surprised at just how wavy the debris was coming off the asteroid in big chunks. And if the computer processing that looks at this data close up, they can actually count like 30 large boulders just flying away from the surface of that asteroid. So this was, the LiCiCube, which was built by Italy, this was a huge success. This was really showing that small, tiny spacecraft had real utility. It was also kind of nice to actually have proof instead of just looking at, light curves from Earth. Here's kind of what we did close up. And then this is just one of the nice confirmations that we did, that if the asteroid, if we hit it, if it was solid versus if it was just that loose rubble pile, if we hit it solid with the same spacecraft, same velocity, we would change its trajectory very little. But the fact that it's kicking off ejecta is actually giving it more of an effect. And so we were anticipating when we hit it that we would change its orbit around the asteroid. Instead of being 11 hours and 30 minutes, we'd change it by 10 minutes. We actually changed it by 33 minutes. It was a much bigger effect, and a lot of that effect was coming from just it being a loose rubble pile. So we had ground telescopes all over the world looking at the impact. The impact occurred 7 million miles away from Earth. So you could actually see the asteroid as a point of light. As they track that point of light with the star fields moving behind it, they can actually see the impact. So that's from Earth. The moment we hit, we kicked off a whole bunch of debris. You're just seeing it loop around there. And then it created a tail. With all that debris, it just created a tail. That tail is 10,000 kilometers long. And that tail lasted almost a year. That was one of the big surprises. Is you see scientists, you're walking down the hall 9 months later, and you just say like 4 words: "Is there a tail?" And they'd say, "Yep." And so this was kind of the neat thing. Just more of the tail. And I think my last slide is more of the tail. But with that, I've got 16 minutes left, so I'm happy to answer any questions. And thank you for coming.
Okay, I will speak English. Assuming that you will succeed and you develop technology to alter the course of those objects in the sky, and those technology sooner or later will become cheap. So, in fact, it will be available not only to your organization, but to others as well. So what does it mean? That all those asteroids in the skies can be not only deflected from the Earth, but can be deflected to the Earth. And it can become the threat for us. How do you deal with such a scenario? Because some organization may use this technology not to deflect asteroids from the Earth, but use it as a weapon of the mass destruction. Thank you.
I think the big thing, none of these you're hitting big objects. It's like trying to hit an oil tanker ship with a speedboat. You know, people would notice if other countries were trying to hit asteroids deep in space to change their trajectory toward Earth. And the uncertainty, I think it's a whole lot easier to try to divert something away than to try to precisely direct it toward. I think the scenario is not really plausible in terms of doing anything of any size that would do any damage.
Into the weapon.
Yeah, but
I just think that that should be also considered.
Yeah, but
as a threat.
So planetary defense is civil defense. It's nature, like the way our government is structured. If it's nature that's impacting the public, that's civil defense. That is NASA. If it is an aggressive entity threatening, the United States and the population, Earth has other populations as well. But at that point, if the military noticed that other entities were sending missions into deep space, they would have a keen interest in knowing what it was, and if it was a threat, to stop it. And it's no longer a civil defense issue. It is a military issue with those assets. So everything here is civil defense because it's nature. It just happens to be two objects are trying to occupy the same space at the same time. Civil defense. And the assets that come with civil defense. But I do not see in the next 200 years where any organization would be having the capability to direct something precisely toward Earth. And if you send it toward Earth, there's still a lot of uncertainty as to when and where you're going to hit. You have to be super precise, and the moment you're not precise, you're putting your own people into the target as well. And I do not believe any of Europe's military or the United States military would allow that to happen.
Hello, I have a question. I'd like to ask you, sorry, my name is Sean O'Kearney and I'm based in Brussels and visiting the Freedom Games. I'd like to bring you back to the slide of the known asteroids and the unknown ones. Could you clarify, if you don't know, how are you able to estimate that there are, say, 45 to be found? Could you clarify that? If we don't know where they are, how come we know how many there are to be found?
So there's a lot of it, you know, how do you know what you don't know? And a lot of that comes with just statistics. And the distributions, you know, they're looking at the data at the rate that we did discover the known asteroids, and they can start using statistics and some other modeling of just scientific modeling of the seeding of asteroids into the solar system to make estimates as to what's left. But it's a very good question.
Hello, my name is Lucas. I have a question about a bit about known and unknown. So you mentioned in one of the slides that you measure about 2 astronomical units away from Earth, all the asteroids, all the objects that are there. And my question is, with something like Apophis, how often does it happen that we have something from outside of that perimeter that we didn't know of, and it crosses potentially our path? And what's the difference in velocity? Because all these asteroids around us, they're probably fairly close. So the difference in velocity between Earth and the asteroids at impact is not that great, I guess. But what if it comes from much further?
So Apophis is a rarity in terms of its size and its approach to Earth. And I don't know about velocity, but they're all, you know, they all tend to have velocities that are measured in, you know, DART hit Dimorphos at 6 kilometers per second. We only put, you know, the rocket only put about 1 kilometer per second into velocity. It wasn't like just the natural occurrence of asteroids and Earth, they tend to have natural impact velocities that are measured in kilometers per second.
Can I ask, how can we know that the asteroid is not going to burn in the atmosphere or bounce off the atmosphere going to space? Do we measure it and know it from the very beginning, or they are hitting the Earth always at the same angle and speed? Yeah.
So, you know, things do burn in the atmosphere, and depending on a certain size, it will, you know, that what you saw with Chelyabinsk, it kind of self-heated and exploded in the atmosphere. You know, other things are much more solid, and they'll just tend to ablate a bit as they come through the atmosphere. And the worry is that something would come in, you know, if it's big enough, it will come in solid into the atmosphere. If it's smaller or breaks up into pieces, there's a chance that it would do what Chelyabinsk did and just explode in the atmosphere, and you just have the shock wave.
Hi, I've got a question. I'm here. Hi, hello. What kind of effect would have a nuclear detonation on an asteroid if we would be able to detonate it in space?
Yeah,
because you said that when we fired this dart at 6,000 kilometers per second, it changed or altered the velocity of the object by some extent, and what kind of the effect would have nuclear detonation have?
So nuclear gets a lot of discussion and modeling. It doesn't get, we can't do, it would be very, very difficult, and it'd have to be highly coordinated to do a test. But one of the, when people first started talking about asteroid defense, they said, oh, just send a nuclear bomb up and blow it up. And people model that, and it breaks it into many, many pieces, but then you have a problem of many, many pieces. And so the one graphic, I thought it would come up in this package, but it didn't, is they actually don't try to blow up the asteroid with the nuclear shock wave. They actually, the intent is to keep it together, but they change the surface property of the asteroid to keep it together, but to give the energy effect of the nuclear weapon. So it's still, that's something that gets a lot of modeling, a lot of presentation, a lot of discussion as to how you would do it. But the early answer of just the Bruce Willis where let's just put the movie version where you just say let's drop a bomb on it and blow it up. That's not the scenario that people talk about with a nuclear explosive.
My name is Piotr. I'd like to ask you the question based on the first topic. How do you predict that the asteroid which would change the direction doesn't interfere with another planet or another asteroid which can come to the Earth and become a danger?
So that is, for this test that we did, every time you go back and look at old interviews with the science team, one of the first words out of their mouth is, number one, this asteroid is not a threat to Earth, and after we hit it, it is not a threat to Earth. But this test, DART is Double Asteroid Redirection Test. The intent of this test was how much, could we change the trajectory by momentum transfer, and by how much? And and so we did the measurement, and it's, while we changed it half an hour in its 12-hour orbit around the larger asteroid, when you do the math, we're changing it about 3 or 4 millimeters per second. And so that's the data that we have at this point. It's for the future to determine, when would you hit an asteroid and what direction would you try to apply that vector of, several millimeters per second. And the key thing, several millimeters per second is not a lot. But if you have time, that key thing was how much time do you have, and you saw that x-axis was in years. You need those millimeters per second over several years to get that body that's about the size of this room on a safe trajectory away from Earth. But that's kind of the subject of the future.
A follow-up to my question, again, me.
Okay.
My question aimed not to Bruce Willis, this type of asteroid, blowing it up, but I was asking about how much effect it would have on the velocity of the object, because as I imagine, this DART system only changes it by a few millimeters, as you just said. And if we would use nuclear-grade weapons, how much it would alter the speed or velocity of the object? And regarding to this DART test, could it bounce the smaller object from the orbit of the bigger asteroid that you were just showing? And the second question, are some of the technologies even considered that would place some engines, ion engines or other engines, maybe nuclear engines, on the object and just blow them away from the orbit, as on one episode of Dexter's Laboratory?
Yeah, number one, my job was to hit an asteroid with a spacecraft, so that's what I know. The parts of nuclear, I get pretty, not deep briefings on, and I really don't know what the effect, how many millimeters per second. The one thing I can point out is that chart of I call it the tools in the toolbox. They use nuclear for the big asteroids. And so they're not really, it's not a tool that's meant for everything. So if it's a small asteroid, they would just look at kinetic impact or civil defense. But if it's the large asteroid, then it becomes, nuclear becomes an option. But I don't think that they're really out to give it a big oomph measured in meters per second. I think you're in danger of your asteroid breaking apart, and you'd have a multi-part problem at that point. So I would be speaking out of my depth if I said I had a precise answer. Okay, thank you very much.
Jedzą kanapki z kawiorem.
Nadzwyczajna kasa.
Obrażanie dziennikarzy telewizji polskiej.
Chodzi o działania polityczne.
Przygotowanie ofiar dla pedofilów.
Für Deutschland.
TVP Info. Włącz się na nowo.
Radość, nadzieja, życie, wyzwanie, pasja, pamięć, zaufanie, pokój, jedność. Słowa tworzą świat. Polskie Radio. Źródło wiarygodnych informacji.
Plany biznesowe powstają z marzeń. Dlatego nie ma dwóch takich samych firm. Jedni chcą działać na całym świecie. Innym cały świat mieści się w dłoni. Sukces biznesu to nie tylko jego wielkość, ale też szczęście, jakie przynosi ludziom. PKO Bank Polski.
Uwielbiam szycie w sieci. Wczoraj podszyłem się pod wnuczka, wieczorem uszyłem intrygę na apce randkowej, a dziś planuję grubymi nićmi szyte oszustwo z promocją. Tak się szyje.
Na oszustów są sposoby. Zapoznaj się z poradami ekspertów na niedajsiepodszyć.pl.
It's not always easy to recognize. It may look like this, or like this. It may be a burden, but it is a responsibility that we embrace nonetheless. But if it means this for one person and this for someone else, maybe it ultimately means being there for one another. It isn't handed to us, but we know where to find it. And how it feels, how it tastes, and what it sounds like when we finally have it. It means different things to different people, but for many, it means everything. And if we all fight for it, it will eventually bring us together.
Ihrer Ausreise
Polskie Radio.
Jedynka.
Rodzina spółek Pelion to 12 tysięcy osób pracujących w ponad 300 spółkach w Polsce, Szwecji, Wielkiej Brytanii i na Litwie. Jesteśmy liderem w branży ochrony zdrowia. Od 1990 roku dbamy o długość i jakość życia. Pracować z nami możesz w jednym z 7 obszarów.
Dziś Nowy Jork, jutro Londyn. Za chwilę Paryż, Warszawa, Berlin. Na całym świecie kultura pulsuje rytmem. Wystarczy tylko włączyć dwójkę. Dwójka, Polskie Radio. Jesteś na miejscu.